Hi, I'm Ben-Yaakov. This presentation is entitled Infrared Temperature Sensor for Power MOSFET. Now, we know that the limiting factor of MOSFET operation or power MOSFET operation is the junction temperature. That is, we are not supposed to get to it or reach this temperature. And also, it's very important to realize that if we are too careful and we cut off the current at a low junction temperature, then we actually not utilizing the power potential of the converter. That is, if we have a converter, we better design it in such a way that we can approach a high temperature of a junction and thereby from the same converter get the highest possible power. Now I'm showing here the equivalent circuit, the thermal equivalent circuit of a MOSFET. This is a power MOSFET, showing it on the two sides. This is the lower side or the bottom side, you might say. This is a metal tab which is used to pass the heat to a heatsink. And then we have the upper side, which is actually plastic. And the equivalent circuit, the thermal equivalent circuit, will look something like that. We have here a current source that represents the power dissipated within the unit. And then we have some heat capacity, and this is the thermal resistance between junction and case. This is this case here, this metal tab, and this will be the heatsink, say, temperature. On the other side, we have also a thermal network for the resistance, thermal resistance and thermal capacitance of this plastic part, which is then exposed to the outside, to the ambient. So there is another thermal network on this side too. Metal part is clamped and covered by the heatsink or first by the thermal pad. What is exposed is really this side here, this plastic part, the upper, the casing of the transistor. So it is possible to measure the temperature of the MOSFET by an infrared sensor. And here it is. The idea is that if we have a transistor operating and we have a infrared sensor which is sensing the temperature from a part, then we can actually get information about the temperature here, and then we can actually estimate what is the junction temperature. It's not simple. I'm not going into these details in this video. Now, the commercial IR temperature sensor available are based actually on a thermocouple. Now we know the thermocouple is a temperature sensor by itself. We have two metals and there is a junction here. This junction is exposed to the temperature that we want to measure. And then it actually developed a voltage, which is a function of this temperature. However, whenever you build a thermocouple sensor, you do have a reference junction. There's no escape. For example, if I connect these 2 points, say, to an amplifier, and these are copper wires, we have another junction here. So what you're actually measuring is not this temperature, the sensing temperature or the sensed temperature, but rather the difference between the sensed temperature and the reference temperature. So there is always a problem with the thermocouple that you have to worry about the reference temperature. You must know it, otherwise you have an error, or you can actually control it. And this is what is done in, say, commercial thermocouple meters. I'm not going into it also, but this is a problem that one has to take into account when considering a thermocouple temperature sensor. So the infrared temperature sensor is basically based on these thermocouple junctions. However, we have many of them. They are fabricated on a integrated circuit, and these will not be just metal with some other material, which again I'm not going into it because it's not important from the operational point of view. But the concept is that we have many junctions connected in series, so therefore we can get a higher voltage. And then we have the infrared radiation impinging on these junctions, actually heating them up. And then we have the reference temperature that we have to worry about, because what we are getting here is the difference between the sensed temperature that we are interested in and the reference temperature. And here we have a cross-section of a very basic infrared sensor. We have the thermopile here. This is the thermopile element. It is connected to the two output wires. Okay, this will already be like copper wires. And so therefore we have inside a reference temperature, a reference junction, I should say. There is an opening here for the infrared ray to go into the thermopile, and usually there'll be a filter for the range of temperature that is relevant for sensing the temperature or that the thermopile is sensitive. And here we see the spectrum, and you see that for temperature of say 300 Kelvin, and this is the range we are interested in, say 300 to maybe 400 Kelvin, then the range, the relevant range of the infrared would be between say 6 micrometer to 16 micrometer, and this is radiation from a black body. Now the radiation is a function of the surface, and this is an issue that has to be taken into account. I'll talk about it later on. And here is a more detailed picture of such a sensor. This is from this website, very nicely drawn. We have the thermopile here, the two connections to the thermopile, and then we have usually a reference sensor. This will be a thermistor, NTC, that actually measuring the temperature of the plate, which is the reference temperature, and the information or the resistance of this thermistor can be actually measured from the outside. These are two wires for the thermistor, so that one can correct for the reference temperature. So this is a very popular approach, although there are some units in which they are doing the calculation inside. Obviously, it entails a much more complicated electronics, and then you get, of course, a corrected value. Now, the simpler sensors don't have it. They have just the thermistor, which is very important for the correction. I'll talk about it later on. And here is a commercial unit, and it is intended for things like medical use, ear thermometers, and some other thermometers. They don't talk about MOSFET, but this will be just the type of a sensor that you might consider using when you'd like to measure the surface temperature of a MOSFET. Now, this is the basic information. I'm not going into all the details. What is important for us is perhaps from this table is the time constant, which is about 32 milliseconds, which is in many applications pretty good, so that you can follow a temperature change in the transistor with a time constant usually around 1 second. So the transistor itself has a fairly long thermal time constant, and so 32 milliseconds would be okay. Now here is the information about the thermistor. This is the range of resistances. Obviously, this range is affecting the accuracy of the reference temperature measurement. And then there is a range for the constant beta. I'll talk about it later on. And this is a constant that is used for fitting the data of a thermistor, that is the resistance as a function of temperature, fitting it to some exponential equation. We'll see it later on. So here is more information about this sensor. We see here the sensitivity, and what we see here is that for a range of about 100 centigrade, the output will be in the range of, say, 10 millivolt. So it's fairly low because the energy entering the sensor is very small, total energy, the radiated infrared. And although there are many junctions, still you get a fairly low voltage, so you do need an amplifier. This is very similar of a thermocouple of two wires, so you need a amplifier, and obviously you have to worry about noise because we are talking about fairly low voltages. Now this is the field of view, and what we see here that it's a fairly narrow beam because of the small opening, of course, and the small size element. And we see that the beam is sort of the effective angle is something like 30 degrees, plus minus 30 degrees. So it's a fairly narrow beam. Now here is some more information about this sensor. Here we see the transmission of the filter, the infrared filter. We see that the pass band is between 6 micrometer to 16. This is what we've seen is really effective range for a black body around 300K to 400K, which is okay. And then we have here a table of the resistance of the thermistor as a function of the temperature. Actually, this is the minimum, this is the maximum, this is the average or typical value. And obviously, all these will have an effect on the accuracy of the reference temperature that is needed for the correction. Now, the error is a function of the operating point. I'm not going into it. It can be easily calculated from this table and the relationship. Now, commercial thermistor data can be fitted to an equation of this type, this exponential equation, and here is beta that has been given in the table that I've shown you earlier. The range was between these two numbers. Again, this will affect, of course, the accuracy. And what this equation says is the resistance at a given temperature is a function of the resistance at the reference temperature, and where here is the reference temperature, and this is the temperature you are interested in. This is for this resistor. All these are in Kelvin, okay? And this is a very well-known equation, and the fitting is pretty good. However, there is some variation here in accuracy due to the spread of the parameters, and therefore the measurement is prone to error. So in actual use, you'll have to mount the sensor on something which is away from the transistor, of course, and then this mounting should have a fairly large thermal capacitance, so the temperature variation of the reference temperature will not be that fast because you need a correction. So you need to read the temperature of the thermistor. You have to calculate the temperature from the resistance. So it'll be better if the temperature variation of this reference temperature will be slow and not that fast. Okay. Now, what you measure is the surface temperature. Now, this surface temperature is obviously not the junction temperature, and there is a resistance, thermal resistance between here and the junction temperature. Also, there is a thermal resistance to the ambient, so the ambient is also affecting what is happening here. Okay, so it's not just the junction temperature, but also this ambient temperature. And then, in order to get the junction temperature, well, you have to do quite a bit of estimation here, taking all these variables into account, not to mention that since you measure from the outside, the temperature drop within the die itself from its surface to the actual junction will be a function of the current. So you need also to know what is the current, what is the ambient temperature, and do the correction and estimation back into the junction temperature. So it's not simple, but obviously it can be done. Tesla is doing it. We know that Tesla is using this type of sensor. I don't know for what purpose, but they are definitely using an infrared sensor. Now, if you use a dual side cooling from the bottom and from the top, okay, so you have a thermal pads both at the bottom and at the top. This is the bottom mu, this is the bottom metal pad, and then this is the upper side, also a metal pad. Then, of course, from the point of view of the temperature measure, this is a much better situation. However, this is now white, and so the emissivity is kind of tricky here. So perhaps you'll have to paint it black if you like to use it in a better way. So what are the conclusions here? Well, infrared MOSFET temperature sensing is possible. I mean, there's no question about that. Tesla is apparently doing it in its electric vehicle. The installation is simple because there's no contact, like a thermistor or a thermocouple. You have to attach it. There's perhaps some thermal paste you have to put in, epoxy or whatever. So from the manufacturing point of view, the production, this is a very simple solution and very inexpensive in actually manufacturing. However, there are many issues. First of all, you have to consider the area that you are looking at, so the adjustment is not simple. then it needs certainly need calibration because there are many factors affecting the value of the temperature you are actually sensing. And then there is a question of the reference temperature correction. That is, you basically need another sensor, the thermistor, and you measure its temperature. So, you can actually put this thermistor on the transistor, and that will be it. But then there is this question of construction, of how you attach the thermistor to the surface. So, this is what is complicating. But as far as the measurement itself, it's kind of complicated here because not only that you have an IR sensor, you have also a thermistor to worry about, and then there are some many errors involved in this measurement. Now, the translation of what you measure into the actual junction temperature is not simple. As I've said, it is affected by many things. Among them is the ambient temperature that the case, the plastic part, sees. Many times it is attached to a PCB. Now the PCB is getting hot, so therefore it will affect the temperature of the housing at the top. So it is not a simple thing, and probably you need the calibration for that, and you may have to actually measure the temperature of the PCB to correct for this too if you'd like to get a precise measurement or a precise way of estimating the junction temperature. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.